Radiometric dating is a way of figuring out how old a rock or a fossil is. It can be used to figure out how long ago the fossilized organism was alive. Therefore, it can allow us to arrange fossils onto a timeline. By doing this, scientists can figure out when an organism evolved what characteristics. Fossils are snapshots of what organisms used to be like, but without dating them, we don't know for sure what came first. Perhaps radiometric dating has been most impactful in its work in identifying the famous Cambrian explosion. The Cambrian explosion was a period of time 500 million years ago, when many species of animals came into existence within a very, very short period of time. At this point in time, evolution was happening at a very rapid rate. This is only known because radiometric dating links so many fossils to this specific point in time. In 1956, it was announced that the Earth was 4.5 billion years old, as determined by radiometric dating. This news was a very big deal to the world of science, because it confirmed that there was plenty of time for evolution. It made the theory of evolution more commonly accepted. So what's the science behind how radiometric dating works? Strong interaction is the force that holds together the nucleus of an atom. In this form, it's more often referred to as the nuclear force. It's the reason why protons, who should repel each other because of like charges, are so tightly packed together in the nucleus. A nucleus must be properly balanced with neutrons and protons, or else strong interaction won't be enough to hold everything together. If there's an excess of a neutron or a proton, it throws everything off balance. This is what renders a nucleus unstable. When a nucleus is unstable, it decays or emits radiation. The goal in decay is to become stable. Let's look at this diagram. The black squares represent nuclei that are stable. For example, a nucleus with 2 protons and 2 neutrons is stable, and so it won't emit radiation. If the nucleus is radioactive, its place on the table is gray. This means the nucleus will at one point decay. It's unstable. There are 3 types of decay, and the type that occurs depends on what needs to be done to the nucleus in order for it to be stable. The 3 types are alpha, beta, and gamma. As explained by Mascetta in 1989, beta decay is what is associated with carbon dating, but there are 2 other types of decay that exist. Alpha decay, which is the emission of a helium nucleus from the radioactive nucleus, and gamma radiation, which is the emission of an electromagnetic wave that usually follows the emission of a beta particle. We only need to know about beta minus decay. In beta minus decay, a neutron will be converted into a proton. For those of you that know about quarks, this means that one of the down quarks will turn into an up quark. But you can't just turn a neutron into a proton without anything else happening, so to balance charge, an electron is emitted. This electron is nicknamed a beta particle. This makes sense. A neutron has a charge of 0, which is the sum of the charge of a proton plus the charge of an electron. So basically, nuclei that need to lose 1 neutron and gain 1 proton in order to be stable will go through beta decay. Carbon-14 is an example of an isotope with a nucleus that will undergo beta decay. It has 8 neutrons and 6 protons. If we find it on the diagram, we see that it lies on a gray square. Beta decay will turn it into a nucleus that has 1 less neutron and 1 more proton. 7 neutrons and 7 protons. That's nitrogen-14, and on the diagram, it's black, which means it's stable. Note that the most common type of radiometric dating is carbon dating, but other types exist, such as uranium-lead dating. In carbon dating, it's assumed that the organism being studied had the same ratio of carbon-14 to normal carbon as the atmosphere that surrounded it. This is a relatively safe assumption because of how much organisms need to interact with their environments. But when an organism dies, it stops interacting with this environment. It stops taking in carbon, and the carbon inside of the dead organism goes on its natural course of decay. So how can we convert the amount of carbon-14 in a fossil to the fossil's age? Because we know carbon-14's half-life. A half-life is the amount of time that a half of a radioactive sample will take to decay. For carbon-14, half of the sample will decay in 5,700 years. So basically, if we know the original quantity of carbon-14, we calculate the percentage of that which exists now. For example, if 50% of the carbon exists, one half-life has elapsed, which means the fossil is 5,700 years old. If 25% exists, two half-lives have elapsed, and so on. But carbon dating isn't done by actually looking at the atoms, it's done by monitoring the amount of radiation. It's the same idea. If one half-life has elapsed, half as much beta decay will be occurring than the amount in an organism who just died, because half of the carbon-14 has already decayed. Carbon dating is just one example of how taking advantage of one scientific concept could help another scientific concept. It has had a tremendous impact on the way that evolution is viewed and studied in the scientific community.